So I recently learned about this really clever way to write down the equation of a circle given 3 points on that circle. So I think it's pretty well known that a circle is completely defined by any three, different points on that circle. So that means if we've got 3 points on that circle, we should be able to write the equation. But if you just maybe use the standard form for an equation of a circle, x minus h squared plus y minus k squared equals r squared, then you've got a lot of algebraic calculation to determine h, k, and r given the points, we'll call them a, b, and c. And this method makes all of that quite a bit easier. Okay, so it's all based off of the following fact, which we'll maybe sketch a little proof of and then do some nice examples. So let's say we're given 2 points A and B. And then after that, we construct two functions f of xy and g of xy, where f of xy equals 0, so that's like a level curve of the function f of xy, is the equation of a circle of diameter, line segment AB. So that means it contains A, it contains B, and the line segment AB is the diameter. Well, that means that fixes the center to be, let's see, the midpoint between A and B. Okay, then g of xy equals 0, so that level curve of g is the equation of the line AB. Okay, so given those two things, then any point C that we're given, we can find an alpha in R. I guess I should say this point is not collinear with A and B. So I didn't write that here, but that's important. Okay, so for any point C, there is an alpha in R such that the equation f of xy equals alpha g of xy is an equation of a circle containing A, B, and C. Okay, so let's maybe see how this works with a nice example first. So let's say A is equal to -2, 0, and B is equal to 2, 0. Okay, but what does that mean f of xy is? Well, let's first write down the equation of the circle with a diameter of line segment AB. So I chose these 2 points, -2, 0 and 2, 0, to make this an easy process. And I think it's pretty clear that the equation of the circle here is x squared plus y squared equals 4. So notice that definitely contains those 2 points, and that's a diameter of that circle. But now in our language over here, we would want to set f of xy equal to x squared plus y squared minus 4. Because, we want our equation to have a 0 on one side. Okay, and now let's see what is the equation of the line given by AB. Well, notice that the line between A and B is simply equal to the x-axis. That's because A and B are both on the x-axis. Well, let's notice that the x-axis has an equation of y equals 0. But that tells us that our function g of xy is simply equal to y. Okay, great. And so this thing down here tells us we should probably look at equations of the form f of xy equals alpha g of xy. In other words, x squared plus y squared minus 4 equals alpha times y. And now let's maybe split these off into a couple of cases. So let's split this up top to the case when alpha is equal to 2. So if alpha is equal to 2, you can rewrite some things and you'll see that you get the equation x minus 1 squared plus y squared equals 5. So I'll let you do the little calculation for that, but that's not too hard. And then the case when alpha is equal to 0, well, that's not a super interesting case. That's the case that we really started with here, and that gives us the circle x squared plus y squared equals 4. And then in turn, maybe we should look at the case when alpha equals -2. And that's going to give us this equation, x plus 1 squared plus y squared equals 5. But now let's get the graph of those three circles on the board so we can get a feel for what's going on here. Okay, so there we've got those three circles on the board. And I think we can see some interesting stuff happening here. So notice if alpha is equal to 2, and so that's obviously bigger than 0, that does this thing that kind of shifts the circle up. Notice our original circle here is in green, and the alpha equals 2 case is in blue. So they still go through these 2 points A, B, but like I said, it's kind of shifted up, and as such, the radius has to increase to deal with this shift up. And I think you can probably guess what's going on here. If alpha gets larger and larger and larger, this thing is going to shift, higher and higher and higher. And in fact, as alpha tends towards infinity, this thing is going to shift towards the x-axis. And in fact, you would get the so-called circle through infinity there that goes through the x-axis. So this arrow indicates alpha getting larger. But then if alpha is negative, that shifts this thing down. So notice it still goes through AB, but this bit has been shifted down and the radius has to increase to compensate for that shift down. And as alpha gets more and more and more negative, or maybe larger but negative, this thing is going to shift further and further and further down. And as alpha approaches minus infinity, this thing is going to approach, well, the x-axis again, which we can visualize as a circle through infinity, just like before. Okay, so that's visually what's going on with this really special case of A and B. And now let's say if you were given some arbitrary C. So let's see, our point C was right here. Well, what would you do? Well, in this case, we would need to shift this blue circle higher and higher and higher until this circle encompassed out to this C point. And, it's reasonable to think that we should be able to attain that. But let's maybe do a little argument to show that it is indeed possible to attain this kind of thing. Okay, so to show this kind of works in general, we're actually going to perform some transformations on the plane to simplify our setup. So let's say we're given arbitrary points in the plane A, B, and C. So the first thing that we're going to do is apply a translation to the plane that puts the midpoint of the line segment AB, so let's see, that would be right about here, to the origin. So we'll rename the points A prime, B prime, and C prime, and now we're in this sort of configuration here. So notice everything is translated by the same amount. And then after that, we'll perform some sort of rotation that puts these 2 points A prime and B prime onto the x-axis. So that's what we've done here. Now we've renamed them A double prime and B double prime, and that has rotated C prime over here to what we'll call C double prime. Then the last thing that we'll do is scale until A, well, we're calling it A triple prime now, is -1, 0. And then B triple prime is 1, 0. So in other words, the circle containing A and B as a diameter is simply the unit circle centered at the origin, which makes everything nice. So that's the picture that I have here. Well, that looks suspiciously like the other picture, but drawings on the chalkboard up to scale really look the same. Okay, so what that means is to really prove that this kind of thing works in general requires us only to consider the case where A is -1, 0, B is 1, 0, and then C is some arbitrary point in the plane not collinear with A and B. In other words, not on the x-axis. So let's start with that setup and then show that we can in fact find an alpha that makes all of this work. Okay, so we just argued that via transformations we could take A to be -1, 0, B to be 1, 0, and then C is arbitrary. It is x naught, y naught. But let's recall that it is not collinear with A and B. That would give us some sort of degenerate circle through infinity. So that means that y naught is not equal to 0. Because if y naught was equal to 0, that would be on the x-axis, but the line containing a, b is in fact the x-axis. Okay, so let's see. This means that our function f of xy is simply x squared plus y squared minus 1. I think that's pretty clear. That has a diameter, which is line segment AB. And then our function g of xy is simply y. That's because y equals 0 is the x-axis. And now let's look at the equation. F of xy equals alpha g of xy. So in other words, we have x squared plus y squared minus 1 equals alpha times y. And now what we'd like to do is tune the number alpha that puts x naught, y naught onto this circle. Okay, so how can we do that? Well, let's plug in our point C. But that'll give us this equation, x naught squared plus y naught squared minus 1 equals alpha y naught. But now we can pretty clearly solve for alpha. Notice that alpha is simply equal to x naught squared plus y naught squared minus 1 over y naught. But then plugging that back into our original equation, we can write a more maybe like standard equation of a circle. And I won't go through all of the details, but we end up with something like this. We end up with x squared plus y minus x naught squared plus y naught squared minus 1 over 2 all squared. And then finally equals 1 plus x naught squared plus y naught squared minus 1 all squared over 4. So that's what you get from like completing the square and all that kind of stuff. So now we can check that the point A, B, and C, or the points A, B, and C, all satisfy this equation. That means that they're all on the circle defined by this equation. But that means we've done it. We found an alpha that puts A, B, and C on the same circle, which was really our goal. And then let's say we wanted to go back to our arbitrary choices of A, B, and C. Well, you would simply apply the translation that got you to this point, or I should say the inverse of the transformations that you got you to this point, to this equation of a circle, and that'll give us our more general equation of a circle. Okay, so let's look at an example of this in action. So let's start by looking at an example outline. So we've got arbitrary points here. And I think it's nice to look at this because there are some nice tricks to write down, for instance, the equation of a circle with the diameter AB and so on and so forth. Okay, so let's see those nice tricks. So let's maybe put star here, and here we're doing equation of circle with diameter line segment AB. And so I'm going to claim that that's given by the function f of xy equals x minus a times x minus c plus y minus b times y minus d. So in other words, the equation is that equals 0. That's the function that we need. So that means f of xy equals 0 is the equation of this circle. And so let's maybe see why that works, because that wasn't really super clear to me why that should work, although it's got some nice structure. Notice that we're doing x minus the x part of one of our points, x minus the x part of another point, and then we're summing that with y minus those points. So let's notice if we were to multiply this out, we get x squared minus a plus c times x, and then plus a times c. And then we'll have plus y squared minus b plus d times y plus b times d. And then this is all going to be equal to 0 because remember we're looking at the function f of xy equals 0, or the equation f of xy equals 0. Okay, so now let's maybe complete the square, move some things around, and see what we have. And maybe I'll like skip some of the details. This is really just like an exercise in symbolic manipulation. But you end up with x minus a plus c over 2 quantity squared plus y minus b plus d over 2 quantity squared equals something squared. The something squared doesn't really matter here. But notice we can pull the center out here, and the center of this circle is simply a plus c over 2 in the first coordinate, b plus d over 2 in the second coordinate. But the cool thing about this is that this is the midpoint of line segment AB. So let's maybe do a checklist here. Notice the equation f of xy equals 0 is definitely the equation of a circle, given that we can write it like this. Furthermore, from this representation, well, that equals 0 of the curve, it definitely contains a and b, because we get a minus a here, and then b minus b there. So that means it contains a, and then so on and so forth for capital B. So it's a circle, it contains a and b, and also its center is the midpoint of AB. So if it contains AB and the midpoint of A and B, that means AB is a diameter of that circle, but that's exactly what we needed. Okay, good. Now let's look at the next part here, and that would be the line through AB, or maybe the line which is line AB. So here we can do this as y minus the y part of one point, let's use b, equals slope. So slope will be change of y over change of x. So that'll be b minus d over a minus c times x minus the x part of a point. So we're just using the point slope form of a line. So notice that we can rewrite this and grab an equation for g of xy fairly easily. And that equation will look like this. So we'll have b minus d times x minus a minus c times y, and then plus ad minus bc. So there we have it. So what does that tell us? That tells us our equation f of xy equals alpha g of xy turns into the following more general shape. So we'll have x minus a times x minus c plus y minus b times y minus d equals alpha times all of this. So we have b minus dx minus a minus cy plus ad minus bc. And that would be the expanded out version of this boxed equation down here. And via those transformations, we know that we can choose a number alpha that will allow us to put x naught, y naught onto this circle. And how would we do that? Well, we simply plug in x naught, y naught into this equation and solve for alpha. Okay, so now let's do a concrete example. Okay, so let's use that outline to write down an equation for a circle containing a, which is 5, 3, b, which is negative 2, 0, and c, which is 1, 1. So first off, we're going to write down the equation of a circle with diameter AB. So that'll be represented by the function f of xy, which is, let's see, x minus 5 times x plus 2, and then plus y minus 0 times y minus 3. And really that equals 0. So we argued why that's the right equation on the last board. And then we'll also need the equation of a line through AB. So that'll be represented by the function we'll call g of xy, and that turns into the following thing. So after doing the calculation, you'll see that you get 3x minus 7y plus 6 equals 0. Okay, so there's our f of x equals 0. This is the expanded version of f of x. G of x equals 0. This is the expanded version of g of x. Okay, so that means, well, every circle containing a and b is of the following form. And that's really what all this is about. So it's of the form x minus 5 times x plus 2 plus y times y minus 3 equals alpha times 3x minus 7y plus 6 for some alpha in the real numbers. Okay, great. So now we just need to turn the dial on that alpha so that it includes the point C. And, based off what we said before, what we'll do is plug in the point C here. In other words, in this case, we're going to set x equal to 1 and y equals 1. So that'll leave us with negative 4 times 3, that's this bit right here, plus 1 times negative 2, that's that bit right there, equals alpha. And then we'll have 3 minus 7 plus 6. Okay, nice. But now let's do a little bit of simplification. So all of this stuff on the left-hand side turns into the number negative 14. Okay, and then all of this stuff on the right-hand side turns into the number 2. So that gives us this nice equation, 2 alpha equals negative 14, but that means that alpha is equal to negative 7. Okay, so we've got a number for alpha, and now we can plug that up here. Okay, so let's do that. So this orange arrow indicates plugging in alpha equals, like I said before, negative 7. So let's see, multiplying this out will give us x squared minus 3x minus 10. Then multiplying this out will give us y squared minus 3y. And here plugging in alpha equals negative 7 will give us negative 21x plus 49y and then minus 42. But then we can rewrite that in the standard form for a circle, by completing the square and doing whatever we need to do that. And we'll see that we get x plus 9 quantity squared plus y minus 26 quantity squared equals 725. And so notice that that was pretty simple. I mean, we did a lot of setup here, but the number of calculations we had to do was really quite small. And we never had to solve any equations that were larger than linear equations. Okay, so let's see what we have here. So our circle containing A, B, and C also has the following center. And so that center is minus 9, 26. And it has the following radius of the square root of 725, which I think you can probably factor 25 out of that and maybe some other squares. And you can simplify that a little bit if you'd like to, but I think we can leave it like that, that's fine. So I really like this method. It really takes all of the unpleasantness of writing equations of circles if you know the 3 points. So post in the comments if you've seen this trick before or any other maybe nice trick for simplifying a task which is sometimes cumbersome. And if you haven't subscribed yet, maybe consider subscribing. It would really help us out. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.